So I'm going to try to summarize things that you should have learned in chemistry last year, as well as bring in some things from our light topic, which is the foundation for understanding modern physics. So the first thing we want to do is look at the electromagnetic spectrum and realize that this is a spectrum of all light, and it starts with very low energy. Visible light is about in the middle, and then we start going to increasingly high energy. And the common thing to do is to take this visible spectrum and just expand it out so we can see all of the colors more clearly. So there are three different ways to think about the electromagnetic spectrum. The typical way that it will be thought about is in terms of wavelength. And so kind of greenish turquoise light has a wavelength of 500 nanometers. So the scale is in nanometers. So 500 nanometers, microwaves would be about 10,000 nanometers. Radio waves are 5 billion nanometers. And then we go to very short waves. So ultraviolet is 250 nanometers and so forth. So that is generally how you talk about different colors of light, is by identifying their wavelength. But what we are concerned about is the energy of the wavelength. And the way that the things we measure about light is converted into energy is through this equation, which is called Planck's equation. And E is energy, and it is typically given in either joules or electron volts. H is Planck's constant. And F is the frequency. And you might be wondering, well, they're not giving me frequency, they're giving me wavelength. So how do you find frequency? Well, you are going to use the equation V is equal to lambda times F. And in this case, because we're dealing with light, this is actually equal to C. So if I want to figure out where did they get this value 248, the way they got it was they said energy is equal to H times F. And when I solve my light equation, I know that the frequency is going to be C over the wavelength. So I've got H times C over wavelength. And if I am looking at, I just realized I do not know Planck's constant off the top of my head, so I need to go and grab a formula sheet, because my handy dandy sheet I usually use, I gave to someone yesterday. All right, got the formula sheet. So we're just going to plug in the values of everything in order to calculate. So Planck's constant is 6.63 times 10 to the minus 34. This is joules. Actually, let's do it in the electron volts, since that's what our equation is in, or our pink thing is in. So Planck's constant is 4.14 times 10 to the minus 15 electron volt seconds. C is 3 times 10 to the 8th meters per second. And then hopefully I don't have to convert that for electron volts. And then wavelength is 500 times 10 to the minus 9 meters. So for nanometers, I'm just plugging in 10 to the minus 9 for nano. And I think our units should be foreign. So 4.14 times 10 to the minus 15 times 3 times 10 to the 8th divided by 500 times 10 to the minus 9 gives me 2.48 electron volts. So just to show you how the units cancel, seconds cancel with seconds, meters with meters, and so I'm left with units of electron volts. So that is how we generally will convert from wavelength, which is a common way to talk about light, to energy, is by using Planck's equation. Now, just in general, you should know, it's sometimes easy to just think about the trends. I know that gamma rays, those are really dangerous, and so I know that this is the high energy side. Radio waves, not too scared of those, so this is the low energy side. And I can also tell by looking at this equation that frequency is proportional to energy, so that means that this is the high frequency side, and that means this is the small wavelength, because when I look at this equation, I see that wavelength and frequency are inversely related to each other, or I can see here too, inversely related. So corresponding low E, low F, and then long wavelengths. And again, I can look at the numbers and I see, oh yes, these are long wavelengths. So that is the first thing I need to understand, is the conversion between wavelength or frequency and energy. The second thing that I want to understand, and this is a little bit ugly, I was talking earlier about orbitals. First of all, I wanted you just to see that these are the shapes. These are solid or three-dimensional shapes, and this is what an s orbital looks like unhybridized. I have 3 p orbitals. They are dumbbells oriented along the x-axis, the z-axis, and the y-axis. And then we kind of go crazy. So these are the d orbitals. Again, they're solid figures. These are the f orbitals. And I think I was reading somewhere a couple months ago that they have shapes for g, h, I, and so on. All right, so instead of the orbitals looking like these nice circles, they are actually these shapes. But those shapes are kind of hard to draw, and so that's why we draw circles. Now, the next thing we need to, so I just thought that was cool, and you guys might be interested. So this is the nucleus, and we talked about energy levels. The closer I am to the nucleus, the lower my energy level. And one way to think about it is with these circles, here's the nucleus, first energy level, second energy level, third energy level, fourth energy level. But when we start talking about transitions, I actually think it's easier to see it expanded like this. And so first of all, here's my first level, so that's green. Here's my second level, that's turquoise. Third level are these 3, that's my purple. And fourth level, that's kind of grayish blue, that's my fourth level, and it keeps going up. So on each level, I have different types of orbitals. I have s orbitals, p orbitals, d orbitals, f, and so on. And generally, electrons, their ground state is filling lowest energy, so that's down here, up to highest energy. And we look at the number of electrons in a neutral atom, and we kind of fill from there. So one of the colors that we looked at was helium. And helium is the second atom, so it has 2 electrons. And so it's going to have 2 electrons in this 1s level, and that's all it's going to have. And so this will call, and electrons that are in the outermost shell, those are called valence electrons. So helium's not too exciting. We will, let's look at something else, and we want to look at neon.
Mrs. Hall, please.
Sorry about that.
Please call 6016, Mrs. Hall, 6016.
That is so annoying when they make announcements when I'm trying to make a video. So neon is the, I believe it's the 10th element, but I'm just going to look it up. Yep, 10th element. And so we are going to put electrons from lowest energy to high. And so I've got 2 in the 1s. I put 2 here, so that's 4, 5, 6, 7, 8, 9, 10. So I have filled my electrons. Okay. Now, the idea is I come, and I can show you that here. So I've got 1, 2, and then 3, 4, 5, 6, 7, 8, 9, 10. So I've completely filled that shell. I can do it either way. You might want to know, why am I making these funny things? That's for spin up, spin down. We'll talk about that when we do magnetism in electricity and magnetism. Okay, so this represents ground state. So the idea is I can hit my ground state electrons either with a lot of electricity, or I can hit them with light. So we're doing photoelectric effect. So I'm going to show hitting them with light. I'll do it orange. And I will hit one of these electrons in the valence shell, and I will excite it. There are rules for this, but I'm just going to show it going up to here. So it could go up there. That would be one possibility. And another possibility is that it could go even higher. Like I said, I'm actually violating rules, but that's okay. So when I remove the light, so light is now gone, the electrons will go back to where they were. And the only way they can do that, the only way they can do that is if they give off a certain amount of light. So when this goes back, this will then give off a photon that is exactly equal to the difference in energy. So that difference in energy is equal to the energy of the photon. Okay. All right, so that is the basic idea. When I irradiate or hit a compound with light, then I will excite an electron to a more excited state, and then when it comes back down to the ground state, it will release energy exactly equal to the gap, the energy gap, or the change in energy. So this is a model of what that looks like, and they're doing the circular model. So there are 4 possibilities, and we want to just explore this. I can see that on all of them, I've got 2 electrons in my valence shell, and I'm going to hit them with light. And you can kind of see from the visual, that's one light, that's another light, another light, another light. So I can see that those are not just bad drawings, that they are intentionally drawn the way they are. So in the first case, I jump 1 level. I go from this level and I jump 1 level up. Okay. In the second case, I go from this level and I jump to a higher level. Okay, so think about how that might have happened. In the third case, I just eject an electron and this becomes an ion. So eject electron. And it has this amount of velocity. And in the last case, I have also ejected an electron, and it has this amount of velocity. So that's kind of the basis. I think from just this, you'll be able to answer the questions. And so there we go.